All right, so we're going to talk about implementation. First, we're going to talk about how to represent general graphs with code. So if you look at different graph implementations, they probably represent graphs differently. Okay. Now, for vertices, it's probably pretty obvious that each vertex is probably going to be represented by an object, a vertex object. Um, so the main question is really how do we represent edges? And there are at least two very common techniques that are used. One is called the adjacency list. The other is called the adjacency matrix. And as a matter of fact, we've seen this before when we were doing the sparse matrix assignment. So this is an example of the adjacency matrix, and it looks just like a matrix. So, but let's look at the graph first. And this graph just has three vertices, A, B, and C. There are two outgoing edges from A to B and A to C, and then there's one outgoing edge from C to B with a cost or weight or whatever we call that number. Right? In order to represent this graph in an adjacency matrix, so the I guess this is the row heading. The row heading and the column heading, they're the same. They represent the vertices. Now I think this is the row headings. They represent the source vertex or source vertices or the from vertices for the edge, and the column headings, they represent the to or destination vertices for the edge. So for example, from A to A, there is no explicit edge, but we know for Dijkstra, the distance between the same um, vertex is 0, so we might want to put a 0 there. Anyway, so to represent the edge 3 from A to B, so we put in this cell from A to B the number 3. Right? And to represent A to C, we say A to C, and the weight or cost is 6. Now, for anything that's not connected, for example, there's no edge from B to A, then we either leave it blank or set it to infinity or set it to none or something like that. So it should look kind of familiar. Um, and now, uh, when do we use adjacency matrix? As we saw in the sparse matrix assignment, this kind of matrix is good if many of these cells, if they are few, meaning the graph is very dense or many of these vertices are connected. But if the graph is sparse, then very few of these entries are actually filled, and representing the graph using adjacency matrix in that case would be very wasteful. And if that were the case, then the adjacency list would work better. So for the same graph, then for each of the vertex, we just keep a list of all of its neighbors and possibly, well, and with the weights or cost, right? So for A, it has two neighbors, B and C, and the going to B, the weight or the cost is 3, going to C, the weight is 6, and same thing for C, going to B, it has a weight of 7, and then for B, it has no neighbors as far as the directed edges go. So again, adjacency list is a lot more efficient if the graph is sparse. And because graphs are mostly sparse, this is the more commonly used approach. And that's what we'll do. Now, even after we settle down on implementing adjacency list, there are different approaches how to implement adjacency lists. And if you're interested, you can look at all the possible options listed in the Wikipedia. And as a matter of fact, the readings use one approach, and that it does not actually use an explicit edge class or objects, even though it will later for a different problem. But anyway, so in my implementation that I am going to present here, we're going to use explicit edge class and objects. right from the beginning because it's actually more general, and it kind of corresponds better to the mathematical definition of graphs, which is a set of edges and vertices. And then it can be used to solve more problems because, well, we'll need it later anyway. So that's what we'll do. So before I show you the actual code, I'm going to present to you one more graphical or visual representation of these vertex and edge objects. So these are just actual, well, they are vertex objects. And obviously there's going to be a vertex class. It has attribute ID, which is, A, B, or C. And then it has a list, or rather probably should be a set. But anyway, a list of outgoing edges. Right? And these edge, they actually would hold a reference or a pointer to the actual edge objects. And as you can see, this edge kind of represent the edge going from A to B, and this edge represent an edge going from A to C. And that's what the vertex A, that's what's in its outgoing edges. And then the same thing for C. In its outgoing edges, it has a reference to an edge object that represents the edge going from C to B. Well, as you can kind of see, there are out edges, there's no incoming edges. And for the problems that we're going to solve, we don't need incoming edges. But for certain other applications, we might need it. Anyway, so moving on to the edge objects. So for the edge, it really helps a lot if we know where the source vertex of the object and the destination vertex of the object, and obviously its weight or cost, right? So for the source vertex and the destination vertex, they're going to be stored as a reference. So that's why you see these pointers. So for the edge A to B, the source is A and the edge is B. And another example, is for the edge from C to B, the source would be the vertex C, and the destination vertex will be the edge, would be the vertex B. So that's edges. Now with that, we are ready to talk about the actual graph class. Now we know the graph is composed of vertices and edges. So what is a good data structure to store all the vertices? Well, the very common use case for vertices is that given the ID, now remember the ID comes from the client code. So given an ID, let's say A, we want to find the vertex for that ID, and we want to do things with it, such as looking for its shortest path, etc. Right? So then very often the frequent operation is to find the vertex object given an ID, and the best data structure for that would be a dictionary, right? So with that, the key then would be the ID, and then the value for the dictionary would be the vertex object itself, and that's what I constructed here, and that's what vertices is pointing to. And then similarly for edges, we're going to have a dictionary that kind of can, given the edge ID, we can look up the actual edge object. Although I believe we're not making a whole lot of uses for this edge dictionary yet. So now we're ready to look at the code, which I already typed up. So I'm just going to go through the code and explain what it is. So this is the vertex class. Now inside it, it has a nested class called path, and this kind of just holds information specific to Dijkstra. And we'll talk about it when we get to Dijkstra implementation. All right, so anyway, the initializer for the vertex, it just takes a ID from the client. Now, the client can choose whatever it wants for the ID. It can use a number, it can use a string, it can even use any kind of user-defined types, or like, and the only requirement really is that it should be unique, and then it should be hashable because we're going to use it as a key in our dictionary. Okay, and anyway, in our example, we're going to use strings mostly, but again, keep in mind it's very flexible thanks to Python. Um, and then we're going to provide for a vertex, for the vertex class, we're going to provide a method called addEdge, which, as it says, it adds an edge from the vertex self, which is the source, to the destination. And the client code would supply the cost. Now, I'll explain where the ID comes from in a bit. But anyway, and then when it's what it does is it instantiates an edge object and then it puts it in the out edges list. And then when it's done, it will return the edge object, which again, I'll show you why that was necessary. It's going back to the graph. And anyway, there's a dunder string representation, obviously. And then I also defined the dunder repre representation, which is kind of just the dunder string. And the reason I do that is because we're going to be printing out, we're going to have lists or, yeah, lists of vertices. And when you print out a string list, the list actually called the dunder repre for each of its elements. So that's why I defined this so that it comes out, you know, when we print the list of vertices, it has more useful information. Now, just kind of a note here, I'm not using the add property thing to define any of these attributes into a property. That is really just for brevity, and we know how to do that already. So I'm not going to show that here, but if we want to do that, we can easily convert it later. Next class, I want to explain the edge class, obviously. So, well, basically, the edge holds an ID, the source and the destination vertices, and the cost, right? Again, same thing for dunder string and dunder repre. Now, I just kind of want to explain how I generate the edge ID here, and the edge ID, and it's given the source vertex and the destination vertex is just the source vertex ID with a little arrow to the destination ID. And the reason I'm defining this as a static method is that it will be used by the graph class as I explain next. So here's the graph class. In the initializer, it takes a ID. It's most likely just a string, and just to uniquely identify the graph in case there are multiple of them. Anyway, the main thing is, yeah, the graph holds a dictionary of vertices and a dictionary of edges. Now, we could use our hash map from the assignment, but Python's dictionary is faster and it's more full feature, and that's why we use it here. Anyway, moving on, the graph class provides two methods. One is to add vertex, the other is to add edge. Right, so to add a vertex, the client supplies an ID, and we create a vertex holding the ID, and then we just add the vertex to our dictionary with the ID as the key. And then for the add edge, we take a source and the destination vertex and the cost. Now, the first thing we do is we look up the vertices, vertex objects given the source and the destination and make sure they are in our graph. And then we ask the source vertex to add the edge, right? We generate our ID that we wrote previously, the edge for the edge. And yeah, we add a destination and the cost. And then once we got an edge back from the add edge method, we put it in our dictionary of edges. And then the dunder string is kind of what you expect. It prints out the ID and all the vertices plus the edges. Now, one thing that's worth noting, oh, actually, before I get there, I just want to point out this colon vertex here. If you haven't seen this syntax before, this is called type hinting. It's basically telling the IDE or static analyzer that this name should be the type vertex. Now, Python doesn't enforce that. So this is, again, called type hinting. And I'm still experimenting with how useful it is. Anyway, the final thing that's worth noting here is that in this particular implementation, I've been very careful not to expose the vertex object or the edge object to the client. So the way for the client to refer to a vertex is really just through its ID. And when we run the shortest path algorithm, we'll return the IDs as well. So these vertex and edge objects, they are not exposed to the client, and they're considered internal to the graph class. So it seems to work so far. We'll see how well that assumption holds. Finally, we have all these classes created, so we should make sure that it works. As usual, I just write a test, even though this really doesn't assert anything. But what I wrote here is I wrote a create graph method that takes the graph ID and then a set or a list of, or an iterable really, of vertices and edges. And then I add each of the add each of the vertex from vertices and add each of the edge from the edges. And what the way that we can specify, ID is just a string, can be anything really. Now the vertex IDs, like I said, it's we usually just use a single letter to identify a vertex. So this is just a string. We specify that we have 5 vertices as u, v, x, and y. So by the way, this is recreating our Dijkstra, the graph used in our Dijkstra demo. So anyway, so those are the vertices. And now as for list of edges, then it's a little more complicated. Each edge is represented by a tuple of source, destination, and cost. So this kind of says an edge from S to U with a cost of 10, so on and so forth. So at the end of this test, again, I'm not really asserting anything. I just want to print out just to see that we initialize everything okay. So I actually typed it out here, and I can actually run this. And there is that ID and the vertices and all the edges. Now I'm going to ask you to actually try to do this yourself. You've seen this graph before from Wikipedia. You were asked to run a Dijkstra on this graph by hand. So now program it. So create this graph in the code. Now, one interesting thing is you see this graph, the edges, they don't have directions. So what can you do? Think about that. And one thing I can think to do is that, and you can add, actually for each of these edge, you can add 2 directed edges, right? One going one way, the other going the other way, both have the same cost. And so that's how you can possibly represent a non-directed graph using a directed graph implementation. Another way is obviously you can design the graph class from the ground up to support non-directed edges.